Hello everyone, my name is Saar, and I'm excited to present my paper, Mini-Batch Robustness Verification of Deep Neural Networks. This work was conducted jointly with my advisor, Drachsler-Cohen at the Technion. So let's begin with the motivation. Neural network image classifiers are widely used across many domains, including safety-critical applications such as autonomous vehicles. Despite their impressive success, they are found to be vulnerable to adversarial attacks, which are small, carefully crafted perturbations added to the image pixels that can cause the network to misclassify, which can be very dangerous. In order to assess the safety of these systems, we use verifiers to formally prove the network's resistance to these attacks. Using the local robustness property, for example. So given a network, an input image, and a set of all image variants within an epsilon distance around it, a verifier attempts to prove that all inputs in this neighborhood are classified correctly. And there are two categories of verifiers. Sound but incomplete verifiers can determine robustness when it holds, but they cannot always determine a violation. Whereas sound and complete verifiers can also find a counterexample when the robustness doesn't hold. So this local robustness property that I just showed you is with respect to a single input image in a single neighborhood. But in order to estimate the robustness level of a network in general, it is common to determine the local robustness for a set of inputs. Most verifiers analyze neighborhoods one by one. And for reliable estimation, though, large sets of inputs are necessary. The larger, the better. So this becomes highly inefficient. Okay, so to mitigate this, our approach to expedite the analysis is to, instead of verify neighborhoods one by one, we verify mini batches of neighborhoods through a counterexample guided abstraction refinement procedure while dynamically learning the optimal batch size. So you see how this is much faster. Okay. So let's dive into the problem definition. A neural network image classifier N takes an input image X and determines which class it belongs to. The input layer of the network consists of the pixels values, which are then propagated through the hidden layers of the network. Each hidden layer consists of neurons, where each neuron applies an affine transformation of its inputs and weights, which is then followed by an activation function. We focus on the common ReLU activation function, the rectified linear unit, which is non-linear, but it consists of two linear parts, the active part and the inactive part. Then at the end, the neuron with the maximum value in the output layer determines the classified class, the predicted class. Okay, so let's define more formally a local robustness. Given an input image X and a small number epsilon, the L infinity epsilon ball around X is the set of all inputs that differ from X by at most epsilon. In practice, this forms an interval for each pixel, represents the range of values it can get. And we say a network N is locally robust in the epsilon ball of X if it classifies all the inputs in this neighborhood the same. There are various techniques to prove local robustness. One example is interval arithmetic, which propagates the bounds of the neurons and determines robustness only if the lower bound of the correct class is strictly larger than the upper bound of all other classes. While this method is okay, it is not complete and it's not precise enough. So instead, we focus on mixed integer linear programming or MILP verification, which is also complete. A well-known example of such a verifier is the MIVerify, a complete verifier that encodes the network computations with linear variables and constraints, and sends to an optimization solver to search for a feasible assignment. During this process, for each ReLU neuron that can be both active and inactive, a binary variable is added to capture the two possible states. And therefore, the complexity of MIP-verify is exponential in the number of binary variables. And remember, this verifier can only be applied one by one neighborhood at a time. And every neighborhood runtime is exponential, so it's not very efficient. Okay, so these definitions brings me to talk about our problem. In our paper, we address the group local robustness problem. Given a classifier n, a set of inputs s, and a small number epsilon, our goal is to determine whether n is locally robust for every x in its epsilon ball, while minimizing the overall analysis time. Okay. So with the exponential runtime, which can make each query highly inefficient, each query to the verifier very inefficient, how can we mitigate this? Okay, so our approach was to, instead of verify neighborhood one by one, we will take an abstraction of multiple neighborhoods and verify them together in a single query. Okay, so the most naive approach to do this is, given a set of inputs, abstract all their epsilon balls. For example, I can take these two epsilon balls and bound them in their convex hull and verify the hull instead of each ball individually. However, because of the over-approximation error, this can lead to spurious counterexamples which invalidate the verification. So a more promising idea is to abstract the epsilon balls of similar inputs. For example, in this subset of cars in CIFAR-10 datasets, I've noticed 4 images that highly resemble each other. Naturally, their epsilon balls are close and may even overlap, making their convex hull much more precise. However, when we tried this approach, we still noticed many spurious counterexamples, along with a very long overhead because of this neighborhood growth. Okay. So our first insight is, what if instead of abstracting in the input layer, we will abstract the neighborhoods in an intermediate layer? Intuitively, this makes sense because neighborhoods tend to shrink in deeper layers because each layer compresses the information while extracting features relevant for classification. So it can make the neighborhood in the intermediate layer more precise. Our second insight is that we cannot simply abstract all inputs in the set because it might lose too much precision. So instead, we divide the set into mini batches, which are small subsets of inputs for which the network performs similar computations, for which we believe the intermediate layer neighborhoods will be close. Okay? So this approach brings 2 main challenges. The first one is how do we know which inputs to put in a mini batch together, and what should be the mini batch size, how many inputs to include? And second, how can we perform an efficient refinement when we fail to prove a mini batch? When we find a counterexample, how do we know whether it is spurious? And if not, how do we know which epsilon ball is non-robust? Okay, so regarding the mini batch size, we applied a multi-armed bandit or a MAB agent, which is an algorithm from reinforcement learning adapted to our settings. So here, instead of arms, we had batch sizes, and each reward is the batch velocity, which is the rate in which the analysis progresses. And this is eventually what we want to maximize because we want to terminate faster, the verification. And in each iteration, when we want to prove a new batch, the MAB agent recommends a batch size. We then construct the batch, verify it, and observe its velocity. And then the MAB agent updates the batch's distribution, which allows him to learn on the fly the optimal mini batch size and exploit it for later iterations. Now, given a batch size, how do we choose which inputs to include? So remember, we want to group inputs that are close in intermediate layers. So in order to approximate similarity in intermediate layers, we used activation patterns. An activation pattern is a binary vector for every input, whose ith entry is 1 if the ith neuron is active in terms of the ReLU state, and 0 if it is inactive. And for every pair of inputs, we compute the Hamming distance of their activation patterns. So now we have distances between inputs. Okay, so to allow dynamic extraction of clusters at varying sizes, we use those distances to apply hierarchical clustering. This dendrogram is the result of this algorithm. And then we represent it as a binary tree of inputs with batch size in the inner nodes. And this way, if we need a batch of size 2, we can simply extract, for example, this batch. But while if we need a batch of size 4, we can take a larger subtree. Okay, so finally, when we find a counterexample, how do we determine whether it is spurious? And if not, which epsilon ball is non-robust? So the answer to this question relies on the way we abstract the neighborhoods. Because with convex L abstractions, we observe that most counterexamples do not actually belong to any of the original epsilon balls, making them uninformative. So instead, we encode the union of the neighborhoods, which restricts the counterexample to fall in exactly one of the neighborhoods. Okay, so these are the key ideas behind our algorithm, BaVerLy, a complete batch verifier for local robustness. Given a network, a set of inputs, their class, and a small number epsilon, so BaVerLy constructs efficient batches. It computes their bounds in an intermediate layers, unify them, verify them, and applies refinement when necessary. It learns dynamically the optimal batch size with the map agent, and at the end it reports for every input in S whether its epsilon ball is robust or not. Now let's turn to the results. In our first experiment, we evaluated BaVerLy on sets of 100 inputs and compared it against the MIP verify, the one-by-one naive verifier. I will walk you through this table one step at a time. So we evaluated two data sets, MNIST and CIFAR-10, on two types of networks, convolutional networks and fully connected networks of varying sizes. We consider the first 4 classes of the data sets and the epsilon values shown here. And we report the verification time in hours, as well as the speed up factor. So as you can see, on average, BaVerLy achieved 2.3 speed up with a maximum speed up of 4.1, reducing the analysis time from 24 hours to only 6 hours. In our second experiment, we evaluated 3 networks across a dataset of 2 different classes. We evaluated the average verification runtime per neighborhood with respect to the input set size. And these results show a clear trend. The larger the dataset, the faster each neighborhood is verified, which demonstrates the effectiveness of both our clustering and similarity, because intuitively larger datasets provide more similar inputs to group and enable the agent, the map agent, more opportunities to learn and exploit the optimal batch size. And you are welcome to check out our paper for additional results. So to conclude, I presented BaVerLy, a sound and complete verifier for group local robustness. BaVerLy analyzes mini batches of epsilon balls with similar network computations and scales the one-by-one verification. And I also invite you to check out our GitHub. And that's it. Thank you for listening.
We have time for questions. So I'll start with a question. So So I noticed that the network sizes are up to few hundreds of neurons. Is that
few thousand?
Few thousands
the larger
of
one is 7,000 neurons. Yeah.
7,000 neurons. Do you? I also assume that you are running these on CPUs, not GPUs, right?
Yeah, because the Gobi optimization is it runs faster on CPU.
Okay. Do you have insights on how to take this to GPUs so that we can sort of scale this, or is that not because typically the actual networks are much larger, right? So and I see that it's a couple of hours. Even though you have a 4x improvement, we still have like large ways to go, right? Do you have? I mean, is there fundamentally something that restricts your methods to not be applicable on a GPU?
I think maybe with MILP encoding, it's a bit a challenge. But if you try, we already tried to apply this method on state-of-the-art verifiers such as alpha-beta count, which works also on GPU. And it's still work in progress, but I think that in the future we will be able to group inputs and terminate faster the verification, but on more scalable verifiers. Yeah.
There is a question.
Yeah, thanks for the great talk. And I'm wondering that whether we can apply this technique to these any architectures like transformer or CNN kind of things.
CNN we showed it works on, but transformers, that's a good question because it's a different architecture. We haven't tried, but maybe we can talk about it later.
Yeah. Yeah. Thank you.
May I ask the next speaker to get set up while you are answering the next question?
Yeah. All right, thanks for the nice talk. So one aspect of efficiency is the batching. That's very cool. I wonder if you've seen observations or have thoughts of whether there's opportunity for reuse across batches in some way in the verification.
To reuse what?
To have some sort of reuse of the verifications across the different batches, if there's an opportunity for that to incrementalize.
You mean a patch adversarial attack?
Right, across the batches, yes.
Yeah, I believe it can be used in other attacks as well. We haven't tried it, but let's talk about it. I will be happy to.
Let's thank the speaker again.